So Boyle's law is P1 V1 is equal to P2 V2. If the pressure goes up, then the volume must go down. They are inversely related. If you look at the equations above, the gas laws above, Boyle's law is the only one that's inversely related, while the rest of them are direct, direct, direct. So we will derive Boyle's law right now, and we will try to figure out how did they come up with this equation. Okay, so again, scientists like to do experiments to get an equation. So here what we have is a syringe. This piston can move up and down. Okay, so we'll start over here in the very end. So what we've done is we've taken a very small volume and the pressure and measured the pressure inside, 1.81. If we release the piston up a little bit, then the molecules inside will have more room, so the pressure goes down, 0.937. If you pull it up some more to 10 milliliters, there's even less pressure, more room. All the way to 20 mils, there's even less pressure, 0.469. Here, when we moved it to 25 milliliters from here to here, the pressure gauge broke, so we don't know what the pressure is inside. So what we will do is we will use the data that we have in the past to figure out what this would be. To do that, we are first going to tabulate the data. So in the beginning, we had 5 mils. So we're going to put 5 mils here, and the pressure is 1.81. Okay, then we changed it to 10 mils, more room, so the pressure goes down, 0.937. At 15 mils, the pressure is even lower, 0.629. 20 mils, the pressure is 0.469. And at 25 mils, the pressure gauge broke, so we'll never know what that is experimentally. Therefore, we have to use this data. When I plotted this data, I put volume on the x-axis because it's the independent variable. I went 5, 10, 15, 20 to 25. And then I put pressure on this y-axis, 1 and 2 atm. Plotting the 5 mils is 1.81, so 5 mils about 1.81, 10 mils about 0.937, sort of, 15 mils 0.629, and so on. Okay, and it looks like as you increase the volume, the pressure goes down. It makes sense. As you increase the volume going to the left, the pressure is lower inside. There's more room, so there's less pressure inside. Okay, less pressure inside. So this is not a line. I mean, this is a curve, so it's very easy. It's very hard to figure out what this is. Okay, if you look at the above experiment, it was linear. Therefore, it was easier for us to use the equation of the line y equals mx plus b. Here, it's a curve, so it's harder for us to model this. So what we will do is we will change this data so this will become straight, okay? And here's how we will do it. If you notice, this is going up, right? So it's directly related. This one's going down, so it's inverse. So what we can do is we can take the inverse of the volume, 1 over the volume, and plot that against the pressure. Okay, and that should give us a straight line. All you have to do is take the 5, and in your calculator, take the inverse of 5, which is 1/5. What is 1 divided by 5 in your calculator? Go ahead and do that. You're right, it's 0.2. Okay, what is 1 divided by 10? 0.1. What is 1 divided by 15? The inverse of 15 is 0.067. 1 divided by 20 is 0.05. 1 divided by 25 is 0.04. Okay? We will not take the inverse of the other one, otherwise we'll come up with the same curve. So we will just write this one down. 1.81. 0.937, 0.629, 0.469, and question mark. Okay, Next thing we're going to do is plot this and try to get, hopefully it'll be a straight line, and it will be a straight line. Okay, so I'm going to plot 1 over volume on the x-axis. This is going to be on the x-axis, and pressure on the y-axis. Okay, I'm going to do, to graph this, the pressure ranges from 0 to about 2. So I'm going to do 1, 2. This is 1, 2. We'll call this 0.5, and we'll call this 1.5. Okay, this one goes from 0 to 0.2, so we'll call this 0.1, 0.2, and we'll call this 0.05, and we'll call this 0.15. Okay, because it goes from 0 to 0.2. Okay, so now the first plot, 0.2, 1.81. 0.2 is right here, 1.81 is up here. Okay, 0.1, 0.937, 0.1 and 0.937 here, and then 0.067, 0.629, 0.067, 0.629 around there, 0.05, 0.469 about there. Okay, so here's your line. It's straight. So now that we have a straight line, you just have to extrapolate. Okay, so the equation of this line is going to be equal to, I'm going to write it up there so I have more room, y equals mx plus b. Okay, again, the y-intercept is going to be 0. Okay, we're going to have on the y-axis, it is p equals the slope. On the x-axis, what is it? It's 1 over v. Okay, solving for m, we can multiply both sides by v. M is equal to Vp, which is equal to, if this is the first condition, is equal to any Vp. Second condition. So V1, P1 would be here. V2, P2 would be where you extrapolated in the future. If they're both equal to M, that means they're equal to each other. So I'm going to flip them because the equation is P1 over V1, so it's fine, same thing. P1, V1 is equal to P2, V2. And this is how the equation was derived, as you can see here. This is Boyle's law. Okay? To use it, all we have to do is use one of these data points. We can use that one, and then solve for the unknown. So pressure is 1.81 atm. Volume is 5 liters. I'm sorry, milliliters. Equals P2 is a question mark. That could be X. And then V2 is 25. So what you're doing is you're figuring out what happens if the syringe gets pulled up, and you have more volume here, 25 mils. So solving for X, all you have to do is divide by 25 mils. That cancels. 25 mils. This unit cancels with that unit. Make sure they match. X is equal to 1.81 times 5 divided by 25 equals 0.362. And the unit left over is atm. So the pressure here, that right here when it broke, is 0.362. 0.362. And that's how you use Boyle's law.